So, Rafi, you asked me number 9. You've had me now for a bit. How do you think I would start this? What probably would I do first before I really did anything else? I would dulp. I'm going to draw a little picture. Did you draw a picture, Rafi? Okay, let me do that first. I'm going to point the ramp for some reason this way, only because as a lefty, I find ramps like that easier to draw. Okay? I would also analyze, just that alone I think is going to help me. I can fill in the 10 degrees, I guess. And I guess it's a maximum height of 20 meters. And then there's also a physics phrase, Rafi, in this question that I would underline because it probably made my question a lot easier. Can you spot the physics phrase that we often target? One of them is at rest, which doesn't appear in this question, but what else? Yeah, constant speed. Because what is constant speed really telling me? As a number, yeah, you're right. Can you say, so A equals what? I would even go like this. I would say A equals 0, whatever. I want to make sure I don't accidentally forget that. What that also means is if I go winner minus loser, it's going to be winner minus loser equals nothing, equals 0. Okay. A says, what force is required to pull the ramp, so to pull the mass up? So I'll put the mass, let's say, right there for now. What are the forces acting on it? Get the obvious one. This was also, the reason I assigned number 9, it was also a nice review for the test you guys just wrote. What else? What else? Look up. I'll get that later, but look up. What else? You know what? There's a rope pulling it. Hey, let's imagine it's a rope. What do we usually call the force from a rope? Tension. You could call it F applied as well, but tension's easier to write that way. Shouldn't the angle be 20? Oh, 20-degree incline. I'm sorry. Who spotted that? Candy for you later. I was looking at the math for some dumb reason, right? Go figure. So far, so good? Now, absolutely components. And you know what? I should have put the mg on this side, because that way when I go components, it's not sitting in my triangle. When we go over the forces test, we will in a couple of days, some of you are going to notice you're drawing these triangles wrong. So the most common mistake that I see, can you all look up? And I think maybe, I'm trying to remember it because I marked your guys' tests a few days ago, but there was a couple in here. They're doing this. Watch. Don't write this down. Now the problem is what just happened. You've changed where the right angle is. You've changed what the hypotenuse is. You've changed everything. And that force there is not parallel to the ramp. I think maybe you did that. Okay? So that's a habit we want to break. I'm going to go down and then straight parallel to the ramp. Dotted line, by the way, is my way of saying its components. If I draw it with a solid line, Grayson, then I'm saying that's an extra force. This is not an extra force. This is me breaking gravity up into its subcomponents. So far, so good, Rafi? Okay. Can you give me, which way is this ramp, this mass moving? Okay. Is it accelerating up? So it's a tie. Can you give me an equation along the ramp? What two forces must be the same size so that I don't have any acceleration? What's pulling it up? Tension. What's slowing it down? Don't say mg because that's not quite right. Yep. What two forces must be equal then if we're not accelerating? For part A, when it says what force is required to pull the mass up, I guess I have to cancel out mg sine. I'll let you do the math yourself, okay? B says, how long is the ramp? Well, you know what? If I actually redraw the ramp, they told me this is 20, they told me this is 20 degrees, and they want, let's call it D for distance. I think that I can do straight grade 9 trig. I think it's, right? Opposite, hypotenuse. I think you can use sine of 20 equals 20 over d. Hey, I have one fraction equals one fraction. Stuff moves diagonally. I think the distance is going to be 20 divided by the sine of 20. Is that okay? Now, C and E are asking the same question. C says, how much work? E says, how much work? But C in brackets, how does it want me to find the work in part C? What does it say in brackets? Okay. Which distance? The ramp. Which force in the same direction as the ramp? It's going to be the tension that we found in part A times the distance answer, whatever you get from part B when you do the trig. And apparently when you do that, you'll get 1,900. Oh, you know what? I can just go like this. It's going to be, are you ready? Are you ready? mg sine 20, that's the tension, right? Yeah. Times, what's the distance? 20 over the sine of 20. I think that's what you'll get in part B when you get the d by itself. Okay? Yeah. And by the way, this 20 right here is actually the height of the ramp, isn't it? In my picture? Yeah. Take a look at what we've actually... D says write a work energy equation. It's the change in potential plus the change in kinetic, because that's another way to do work. But look, not for a new force. In part E, how much work was done if I go the change in energy? I think it's going to be mgh. And can you see that's actually popping out of doing it via force versus distance as well? What we've actually just done is an algebraic proof why work is a scalar. It turns out I could have just gone mgh instead of finding mg parallel, finding the parallel distance, and multiplying those together. That's why I like that question. That's a nice tying everything together question. I think everything else on lesson 1 was okay. Any questions from lesson 2? Yeah, Mickey. Hopefully number, which one? 7? Was it 7 or 6 that I was thinking about? Let's find out. Sorry? 6? Oh, no, 7 is the one okay, 7, good. 6, sure. 6 first. What's it asking me to find, Rafi? For part B. By the way, part A, I'm going to have to write the work energy equation to do part B. So to figure out what equation they want me to write, I'm going to look at part B. What do they want me to find? Work. Work is force times distance. Look at the question. Did they give me a force? Did they give me a distance? No. Okay. Right? I don't see newtons anywhere. Do you in 6? Say no. Okay. Work is also the area under a force versus distance graph. Did they give me a graph, Captain Obvious? No. What was our third definition of work? And this is the answer to part A. Change in potential, change in kinetic. Does this question suggest there's a hill involved anywhere? Or does it seem to suggest that this car is traveling on flat, level ground? Okay. Now, that's not quite the equation. It's written here as an answer. I'm using a slightly different notation, but I'm telling you it's the change in kinetic. What's change in anything? Well, it's final minus kinetic final minus kinetic. It's going to be a half mv final squared minus a half mv initial squared. Make sure you convert that, though, to meters per second. Okay, I'll leave you on to try that. That question I do like. In fact, that's going to be a multiple choice question. I like that question, I like that question, I like that question, I like that question. Number 7, this is also nice because it's going to tie last unit and this unit. That's a good review of both. Okay? So, an 800 holy smokes, that's heavy, kilogram bucket. You know what? That's a cement bucket. That's a big barrel of cement. It's attached to a cable. It's pulled upwards so it accelerates from rest. I would probably underline from rest. At 1.3 meters per second squared for a distance of 30 meters. Write a work energy equation. Okay. Work is force times distance. I do see a distance, 30. I don't really see a force, although I might be able to go mg. For part A, I think I would probably say it's the change in potential plus the change in kinetic. There's the work energy equation. But if you also said force times distance, I'd give it to you. I'm really more interested in B and following. Find the cable tension. Did you get B okay? Did you draw a free body diagram? Did you say what are the forces acting on this big bucket? Get the obvious one. mg down. Why did I draw tension bigger? Which way is this bucket accelerating according to this question? Up. Okay, so tension minus mg equals ma. Did they give me A? So I can actually plus the mg over. Look up, I'm going to cheat. There's your tension. Not only is that a tension, that's the force in the cable. So now I can also start thinking about force times this. Let's keep going. Find the speed. Okay, that's going to be V final. Oh, you know what I'm going to use? Vf squared equals Vi squared plus 2AD. Why? They said from rest, they gave me V initial, right? They gave me the acceleration, 1.3. They gave me the distance. So don't forget to square root. I'd normally list my data and show more work, but I haven't got much room. Okay. It's really D and E that I want to talk about because there's two ways to find work. For part D, I can find the work by going force times distance. Which force? Tension times distance, 30. That'll get you there. Or part E, I can find the work by going the change in potential energy plus the change in kinetic energy. What's change in anything? What's your initial potential? Are you starting out on the ground? Say yeah. What's your initial kinetic? Are you starting out at rest? So actually the work is going to be mgh final plus a half mv final squared. You found V final for part C. H is 30. You should get the same answer for E and D. And again, what we're really saying is my bigger work equation, the work energy theorem, change in potential plus change in kinetic, it's mathematically equivalent to force times distance. Just depends if I have a force or a distance or if I have the change in energies. Is that okay? Yeah. I'll let you try that. Okay, I'll still go over it another bit in more detail if you get stuck. Power and efficiency. This is actually the last lesson in this unit in terms of teaching you new stuff. Lesson 4, which I'm going to do Tuesday, is actually one that I could stick in anywhere. I do it in this unit. It's tricks on graphing and how to read graphs. Anyways, power. The word power is used in a variety of ways in our everyday language, but in physics it has a specific meaning. Power is the rate at which work is done. It's how fast you're doing work. Anytime I talk about the rate at which something is done, those of you that are in calculus will soon learn anytime we're talking about the rate, we're talking about dividing it by time, which means if it's the rate at which work is done, power is work over time. Work, scalar or vector? Scalar. Time, scalar or vector? Power, scalar. Units, power is measured in what? What? Now, you know what? It's actually a joule per second, work over time, but we've given that unit a name. We call that a watt. It's named after James Watt, who actually really shouldn't have a unit named after him. He's not that good a scientist. People say, well, he invented the steam engine. No, he improved the steam engine, and he improved its efficiency, and the Brits wanted more units named after British people, so he's got a unit when other scientists don't. A 60-kilogram girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. What's her power output? Well, power is work over time. What kind of work did she do? She ran up a flight of stairs. When you run up a flight of stairs, Are you changing your kinetic or are you changing your potential? Yeah. Really, it's going to be mgh over time. $60 times 9.8 times 3.32 divided by 2.6. She generated about 751 watts of power. How could she generate less power? And again, power really is what we mean by tiredness. How could she do these stairs, the same set of stairs, and not feel as tired? More time. The down back of the field stairs that have such a shallow angle, that's what that's designed to do. A shallower angle, because they could have made the stairs really steep because it's the same change in height, Nate. They made the stairs really shallow, same change in height, but it takes you longer to walk them, not as tiring. Or you could sprint them and you'll feel more tired, okay? But it's why most stairs are around the same steepness. We've done the physics, we've done the math, and we found a comfortable level of power that most people can generate. Walking. And it's also why if you run a set of stairs, you get tired pretty quick. If 1 horsepower equals 750 watts, what's her power output in horsepower? Well, 751 watts, almost exactly 1 horsepower. Horsepower is the imperial unit of power measurement, the same way gallons measure volume, the same way feet and inches measure distance. The metric unit is watts. The horsepower was originally defined by James Watt. James Watt didn't invent the steam engine, but he improved it, and he was trying to sell it. The reason James Watt has a unit named after him, he was a great salesman. Because, Jenny, he was approaching farmers and he was saying, look, I have this engine and I think you could use it. He was approaching factory owners and saying, look, I have these engines and I think you could use them. Yeah, and they had no context to put them in. And so what did he say? He told them how many horses it could replace. That's really what horsepower is. Oh, this motor has 4 horsepower. And now the farmer says, well, I know how much work I can get out of my 4 horses in one day. Oh, you're saying it can do that much? Yes. Now, it's not quite accurate, but it was a brilliant sales move because now farmers had some kind of a context. In fact, it was such a good sales move. Joseph, do we still use horses in industry today? But how are cars measured? Car engines are given still in horsepower. Really? Yeah, oh, well, yeah, this has 350 horses under the hood is the joke we make. So, good salesman. Example 2. How long would it take a 5 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? So motors are often still measured in horsepower. So you have some kind of an elevator. It's got a little 5 horsepower motor, and you'd like to know how long this will take. Or you're a crane operator, and you've got a little winch, and it's got a 5 horsepower motor. What do they want me to find? Hey, let's start deficking. T equals question mark? What's that 5.0? Power. Wrong units, though. So I'm going to say this. Power equals 5 HP. I want, remember unit conversion? I want horsepower to cancel. I want watts left behind. By the way, if I ask you to go from horsepowers to watts, I will give you the conversion factor in the question, so you don't need to memorize this, Nate. But I gave you the conversion factor 1 paragraph above. How many horsepower is how many watts? It's 1 paragraph above. How many horsepower is how many watts? Can you get how many horsepower is how many? Sorry? 750 watt is how many watt? That's going to go right here, is how many horsepower? Sorry? I need the whole I didn't know where to put the numbers. You can't just quote number. I need the units so I know where to put them. Okay, so how many watts of power does this motor have? 5 times 750 divided by 1, which I'm not going to bother doing. What do you get? Is it 3,750? Okay, power. What's this question asking me to find? What did they give me? Power. Is there an equation that has power and time in it? Well, yeah. Power equals work over time. Let's get the T by itself. Oh, by the way, this equation, power equals work over time, is the last equation on your formula sheet in this unit. Hey, is this 1 fraction equals 1 fraction? Yeah, power is over 1. So Grayson, technically, work over power. Now, work is measured in joules. Did they give me joules in this question? Do you see joules anywhere in this question? No? All right, guess we got to break work down. What are our definitions for work? Work is what times what? Force times distance. I do see a distance. I see that we're lifting. Oh, when we're lifting, what force are we doing work against? Did they give me the mass? Okay, they don't need to give me the 9 point. I can do this. This is going to be force times distance over power. Which force? Fg. And from last unit, what's Fg as an equation? Get the obvious one. What have we always put there? I haven't just put the word gravity. What have I put as an actual expression? Okay, so Rafi, the time is going to be m times g times, instead of d, let's call it h. Oh, that's also the change in potential energy, which was my other definition of work, over power. 500 times 9.8 times 30 divided by 3,750. What's the fastest, if we rev this motor full up, what's the fastest that we can lift this safe up? Can't be done any faster. Do you get 39.2? Units, time. Okay? With a 5 horsepower motor shack, it's going to take you 39.2 seconds to lift that safe up 30 meters. You can't do it any faster. In fact, it'll probably take you longer. This is assuming that that motor is 100% efficient, and it's not. It's probably giving off heat and noise. So even though it's rated at 5 horsepower, you're not going to get 5 horsepower. Even though it's rated at 3,750 watts, you're not going to get 3,750 watts of useful work. A lot of that energy is going to go into heat and sound and other dissipative energies. By the way, power can also be related to the applied force as follows. Power is work over time. We said that work is force times distance. Look up. Circle that. What do I measure distance in units? What do I measure time in units? What is meters per second, actually? You know what? Another way, and this is not on your formula sheet, but I've just showed you how to derive it. Turns out power is also force times velocity. When do I use that? If they ask me to find power and I don't see work or time, but I see a force and a velocity. That's not on your formula sheet, but hopefully, Mac, I've showed you, it's actually kind of a clever, fairly good derivation. Yeah, it's meters per second. That's the velocity. I think in your homework and on the big review package, there are questions where it says, how much power would a motor need to lift a mass at 3 meters per second? The force is going to be mg because you're lifting, and the speed is 3, you go force times velocity, something like that. Efficiency. Efficiency means how much bang you get for your buck. It's how much useful work is done as a fraction of how much energy you get out compared to how much energy you put in. There is a symbol for efficiency. It's the Greek letter eta, which looks like a lowercase n kind of written cursively with a long tail. That's an eta. However, I'll be honest, I didn't know that that was the symbol for efficiency. For the first few years, my symbol for efficiency was EFF period, and I still tend to use that, but you can use either. And it's defined as work out divided by work in. W out divided by W in. W out divided by W in. Or it could be energy out divided by energy in. Or it could be power out divided by power in. That's not on your formula sheet, and in fact, I haven't memorized it. Here's what I know. First of all, I have to make sure if I'm calculating efficiency, it's joules divided by joules or watts divided by watts, but never watts divided by joules. Then you have to go find the other power. You okay with that? But you know what? Here is the key. Efficiency in our universe is always less than 100%. You can't be more than 100% efficient. So here's what I remember. Efficiency is always the smaller number divided by the bigger number, because that guarantees that you get an answer of less than 100%. Oh, look up. And then to turn it into a percentage, you multiply by 100%, because this gives you a decimal. So now we're back in Math 8. You'll get like a 0.87, that's 87% efficient, or a 0.56, that's 56% efficient. So times by 100. If you get 1.38, you've done it wrong. No, you're not winning a Nobel Prize. You haven't invented something that's 138% efficient, because that means you've, created a perpetual motion machine. No, I'll have to do that. It doesn't work in our universe. So, unless you plan on winning a Nobel Prize. The reason I say that, I know I used the word out on the top and in on the bottom. There is a question in your future, and I have it in my mind, where just the way it's worded, it's very, very tempting to put the word out next to the bigger number in the question, just by the way it's worded, and to put the word in next to the smaller number in the question. And every year I have a few kids who tell me, oh, and this is 183% efficient. No, it's not. It's not. Don't do that. A typical household light bulb transforms heat energy at the rate of 60 watts. Transforms energy at the rate of 60 watts. But most of this energy goes into heat instead of light. So in the 60 watts of power, Joseph, about 57 watts goes into heat, and about 3 watts goes into light. An incandescent light bulb is only about 5% efficient. Unfortunately, politicians who have a bad understanding of science saw that, and they said, oh, let's mandate replacing incandescent bulbs with the CFC, those little spirally bulbs, because those are more efficient. It is true, those are more efficient. But the problem is they didn't look, Rachel, at the big picture. So, when you put a light bulb in your house, the old kind, the ones that you screw in, the ones that look like this, not the spirally ones, after you turn the light bulb on, does it get hot? What happens to that heat? And the answer is, it heats up your house. Your heating bill goes down by exactly the same amount as the heat given off by that light bulb. The politicians didn't realize, Nathan, although 57 watts, although most of the energy goes into heat, that heat's not wasted if the bulb is indoors. If the bulb is outdoors, sure. These don't work well outdoors. There's a reason why we hardly ever use them. The CFC bulbs don't deal well with moisture changes and cold temperatures. So we still use the incandescent ones outdoors. Hey, wait a minute, Mr. Dueck. What about in the summer? What about in the summertime? Because then you don't want to heat your house up. You want to cool your house down. Fair enough. Fair enough. Josh, what country do we live in? Canada. We live in the in the true, blank, strong, and free. The true what? What? Get your hand away from your chin. The true what? North. We live in the northern hemisphere. We live fairly far north. In the summer, do we have longer days or shorter days than most of the rest of the world? Longer. In the summer, do we use light bulbs more or light bulbs less? So the whole, well, you're heating your house up in the summer, really not very much at all. Unfortunately, the politicians have mandated that we get rid of incandescent bulbs. Actually, I think it was January of last year. They're slowly, you can't find them in stores much anymore. Bad policy. They didn't do the science properly. They really aren't as inefficient as people think. If you're using them outdoors, sure, but you can't use the other ones outdoors anyways. You know where it would make sense, Joseph? In the southern United States, where it's warm year-round, and so even in the winter when the days are shorter, they're still wanting to cool off their house. Fair. The real gem is going to be LED bulbs. So I've replaced in my house most of my bulbs with LEDs. They're pricier, but they're very efficient. A kettle might have 1,500 watts. In fact, the faster it transforms energy into heat, the higher the wattage will be. Example 3, a 250 kilogram mass is lifted at a constant speed. You know what, Rafi? I'd probably underline that phrase, right? Of 2 meters per second for a distance of 12.5 meters. All right. Nate, what's A want me to find? Work. Work is force times distance. Work is also the area under a graph, and it's the change in potential plus the change in kinetic. Is there a graph? Nate, do you see a graph? I'm not using that one. Can I use force times distance? Did they give me a distance? Okay, maybe I can come up with the force. Are we lifting? Oh, then I know which force I'm lifting against. Which force? When you're lifting, which force are you doing work against? The obvious one. Okay, so you ready? Work is force times distance. Which force did you just say, Nate? Gravity. And what's our equation for gravity? When I always said get the obvious one, we never actually wrote F with a subscript of G. We already wrote its formula, which was what? Come on, people, which was what? mg. Oh, and instead of D, what have I been writing this unit if it's vertical? H, right? It's the change in potential energy. Okay, how much work was done? They gave me the mass, 9.8, 12.5. How many joules of work did this motor do? Don't all rush for your calculators at once or anything. I'm looking at you, Anita. Pick up your pencil and start typing. Sorry? That? Work, joules. Naomi, what's B want me to find? Power. Power. Is that right? Is it 30,625? Yes? Sorry, I should have got a confirmation because I saw Shaq looking confused, but that could be his natural state. Shaq, power, what was our equation? Power is what over what? Yes, good recovery. Thank you. Do I know how much work was done, Shaq? Just found it in part A. Oh, did they give me a time? You're scanning the question looking for seconds. Did they Oh! Wait. This was force times distance over time. Psst. Psst. What is distance over time? Meters per, what's that? Not acceleration. Acceleration's meters per second. What is it? Hey, did the question give me a velocity or a speed? Is it a constant speed? Not change? Ah! So I'm going to go, which force? mg, stay with black, Mr. Dueck, times v. There's power. Not on your formula sheet, but derivable. 250 times 9.8 times 2. This is how much power you need to accomplish this job, to lift a 250 kilogram mass upwards at a constant speed of 2 meters per second. If your motor doesn't have this power, it can't do it. You get 4,900, and power is measured in watt. All right. C. Now, that's how much power I need, but let's suppose you looked on the side of the motor and the motor said that it was using 10 kilowatts, 10,000 watts of power. You're only getting out 4,900, 4.9 kilowatts. You're putting in 10,000. How efficient? Efficiency is going to be, since we're talking about power, okay, you made it. Grayson, power is measured in watt? There's some watts, see it? And 10 kilowatts, you're okay, 10,000 kilometers, so 10 kilowatts. I said to you it's always going to be the smaller number divided by the bigger number. So how much power are we getting out? 4,900. How much is this motor sucking from the particular plug? 10,000 watts of power. And then multiply by 100% to change it into a percentage. This one I can do in my head, Mickey, it's 49% efficient. Is that okay? Turn the page. How many more are we doing here? Wow, a few more still. There's going to be homework for this lesson, but for lesson 4, there's no homework. Okay, example 4. A mass of 100 kilograms is pushed along the floor at a constant speed. Hey, Rafi, what phrase might I underline? You go, girl. Of 2 meters per second. If the coefficient of kinetic friction is 0.25, what's the power output? Okay. What does this question want me to find? Which is work over time, which is force times distance over time. Now remember, work could also be the area under a graph. Is there a graph in this question, Nate? No. It could also be the change in potential plus the change in kinetic, but I think I can use force times, well, wait a minute. Did they give me a distance in this question? What did they give me in this question? Are you saying that I can use that trick again? Okay. The real question is, which force? I think we better do a free body diagram. Since I see a coefficient of kinetic friction, I see a mu. You know what? Here's the mass. What are the forces acting on it? Get the obvious one. Is it sinking into the ground like quicksand? Is it flying into the air like Superman? Oh, Grayson, I know which punchline's coming up fairly soon. Just saying. So normal force. What else? It's being pushed. So here's our applied force. What else? Now, look up. Why would this be wrong, and why would that be wrong? Oh, Mickey, preach to me. What? So how big should I draw friction? Exactly the same size as which force in the opposite direction? So whatever you've done in your diagram, but for me, you with me so far? So which force, look over here, I'm going to put a little apply, because it's the applied force times V. I don't know the applied force. Oh, but look. I know another force that has to be exactly the same size as the applied force. Which one, Joseph? Okay, so now power is going to be friction times B. Oh, Grayson, friction is what times what? I don't know the normal force. Oh, but look. Oh! You know what force is the same size as the normal force this time? You preach it, girl. So it's going to be mu mg and then V. I'll stop putting a time symbol. This is nowhere on my formula sheet, but you can see, Rachel, it's derivable. I would consider this a B plus level question, but kind of cool. I'm also assuming that all of you sometime in your life have pushed a kid, say, for example, in an office chair down the hallway, or slid somebody on the benches in the gym, or pushed somebody sliding across at a constant speed. This is what you were doing if you were sliding somebody on a slick floor or on the ice while skating or whatever. The coefficient of friction would be different, but the physics is right here. Okay, I think it's plug and chug time. Let's see. It's going to be 0.25. 100, 9.8, 2. I might be able to do this in my head. Sure. 0.25 times 100 is 25 times 2 is 50. 50 times 9.8 is going to be, is it 490? Yeah. 490 watt. Mm-hmm. You'll never get tired of that joke, will you, Mr. Dueck? Watt joke. Oh, yeah. I just made that one up this year. Note to self, use it for the rest of my career. Watt joke. Really? Oh, man. Tough audience. Tip your waitress. What was that? You guys are wattages? Oh, what did I say? Okay. A girl pushes a 300 Newton box. Okay, this time they didn't give me the mass of the box. They gave me the mg, the weight of the box, because it's in newtons, but easy to use whichever. For a distance of 4 meters. The coefficient of kinetic friction is 0.33. She then lifts the box straight up. What is the minimum amount of work she has done? Okay, now we're actually putting everything together. This is not a power question. I guess if I had then told you how much time it took, we could find how many watts of power. It seems to me this question has 2 parts. Pushing along the floor, and then what? Lifting. I'm going to divide my page into 3 because I think part 1 is going to be pushing, part 2 is lifting, part 3 is going to be add them up because it's a scalar, but I'm not going to need much room to add them up. So I'm going to go kind of like that, and on the right-hand side, I'll do my final bit of work. Floor, lift, total. Okay. I think the free body diagram is the same as I've drawn right here. You're pushing something along the floor. Mr. Dueck, it doesn't say constant speed though. Mickey, that's a good point. It doesn't say constant speed. But what word is that right there? Minimum. That's why I put that word. Because if she was accelerating, she's doing even more work. But the minimum means, oh, she's not accelerating, she's not changing its kinetic energy, she's not adding more kinetic energy because its speed isn't increasing. So we're going to assume constant speed. You with me? So first I'm going to go work equals force times distance. Which force? The applied force. I don't know the applied force. Oh, but look. I know another force if we're talking about minimum work that must be the same size as the applied force. Which one? Friction. And friction, Grayson, is what times what? I don't know the normal force. Oh, but look. Okay, you know what? It's going to be mu mg d. That's how much work she's doing sliding something at a constant speed. It's going to be 0.33. I don't know. Oh, wait a minute. That 3 times 10 to the 2. That's mg, isn't it? Because it's newtons. So, by the way, what is 3 times 10 to the 2? 300? 300 times 4. Don't put a 9.8 in there. That 300 already contains the 9.8, right? Do that one in your head, Mr. Dueck. Okay. 300 times 4 is 1,200. 0.33, that's like dividing by 3. I'm pretty sure the answer is going to be really close to 400. Probably like 399 or something like that. 396. Units, work. Joules. Lift. Okay. Work equals force times distance. Nate, when you lift, which force are you doing work against? And so you're saying mg. And, oh, you know what I've called that vertical distance typically? H. Oh, and I know mg, 300. Okay. Nate, what's h? I disagree. Okay, don't get, by the way, that would be sloppy on a test. We got to, pay attention, right? I think I can do this in my head too, because 3 times 12 is 36, so 3 times 1.2 is going to be 360? Double check me, I hope. Yes, no, yes? Joules? Okay, total. 396 plus 300. Mr. Dueck, those aren't in the same direction. One's horizontal, one's vertical. What one-word response will I give you that begins with the letter S? Scalar. I think I can do this in my head too. 396 plus 300 is 696 plus 60, 754? 56? Hey, as a part B, I could say, if she did this in 8 seconds, how many watts of power? Okay, I could do that. I'm not gonna, but I could. Example 6. A person pulls on a 20-kilogram lawnmower with a force of 25 newtons and moves the mower 4. Hey, this sounds like a lawnmower question. Do you know how I know this is a lawnmower question, even without the picture? Because of the word mower. Oh, yeah. The angle handle is 15 degrees with the horizontal, and mu equals 0.1. Find A, the work done by the person, B, the work done by friction, C, the time. Ooh. Cool. We can handle this. How might I start this? Oh, 7 is also a lawnmower question? You know what? I'm going to pass on 6. Let's go to 7. It's also a lawnmower question. And you guys are getting kind of restless here. Example 7. A person pushes with 75 newtons on a lawnmower, which has a handle angle of 20 degrees. You know what? We should underline the word pushes. And let's here's our free body diagram. I guess we have a force coming in like this. 75 newtons. And I guess the angle is how many degrees? Gotcha. The surface has blah, blah, blah. Okay. What are the forces acting on this lawnmower besides the applied force? What else? Should I draw the normal force bigger, smaller, or the same size as mg? First of all, same size? No, lawnmower question. Mickey, why? Because I'm adding a force which way? Down, so now the ground has to push up extra hard. I'm going to do that. What else? Is there friction? Is there friction? How do you know? What's mu with you? Yeah, so friction. Now, components. We typically call this Fy, and we call this one Fx. It's kind of a weird free body because I have the arrow pointing in, but I'll be extra careful. Okay. It says the motor starts at rest. Find the rate at which heat energy is generated. Okay. The rate at which energy is generated is power. But this is referring to a specific type of energy. Which energy? Okay. Power for heat is going to be work over time. Which work? Heat. Pardon me? Maybe. I heard Josh mutter potential and kinetic. Maybe, but heat. We're talking about work now, not conservation of energy. Which force generates heat? Friction. You know what? My first thought is maybe this is going to be the force of friction times distance, force times distance for work divided by time. Okay. Whew. Friction is what times what? We're going to do this one on a separate line, I think. Friction, because this is a lawnmower, is mu times the normal force. I don't know the normal force. Yeah. Really, Naomi? You need the phone for some reason? No? You're good? Put it face down, put it away. Okay. I caught you right away. I'm sorry. I apologize. You back? Hey, Naomi, what's mu? I don't know. What's mu with you? No. Actually, more importantly, look at my free body diagram. What's pointing up in my free body diagram? Straight up. What's pointing down? And, yeah. You know what? This is going to be mu because everything down gets canceled out by everything up. What if we were pulling up? Well, then it would be normal plus Fy equals mg. I think the normal would be mg minus Fy. I'd have to draw it out, Anita, but okay so far? Mu mg plus, Naomi, did you say Fy? 75 sine 20. What's the friction force? It's going to be, what's mu? What did you say mu was? 0.21? Why don't I put it in here? 0.21 times all of the normal force, which is this whole expression. 25 times 9.8 plus 75 sine 20. How big is the friction force? Did you get 56.8368, blah, blah, blah? I'll go 837. So Anita, I'm going to put this here. Let's keep reading before we go any further. Did they tell me the distance? Please tell me they told me the distance. Yeah, how far? Oh, we're home free. Did they tell me the time in seconds? Don't! Oh. Okay, I found friction, but you know what else I'm going to spend time finding? Time. Holy smoke, you know what? Now we're going back to kinematics. Okay, I can do this. I'm going to draw a little line right here. What's D? 30? Cool. Oh, hey, they did tell me VI, right? Our magic phrase, at rest. What else do I need in order to find time? A. How can I find A? Well, what unit did we just finish? Forces. You know what this is a job for? A good free body diagram. Oh, I have one up there. Look at my free body diagram. Who's winning? Careful. Who's winning? Fx. Who's losing? Friction. So, I can say Joseph, what did you say we're trying to find? Divide by the mass. Friction I already found, 56.837. Naomi, are we finding Fx or Fy for this particular section? Look up. Are we finding Fx or Fy for this particular section? Fx. So is it sine? Of course it's not, right? So it's going to be, what was the applied force? 75 cos 20. Oh, and what was the mass? M? 25? Was it 25? You guys aren't helping. Is it 25? By the way, this is an A plus level question. This is putting what? We've used lawnmower from last unit. We're using power from this unit. We're using kinematics from unit 1. This is the whole course in one question. So I do like this question for that reason. I am not saying I like this question, because I told you on this test, I'm going to drop the components on the test. But for what it's worth to give, I said during the lessons, I'll show you where we could pull components out. Here. Do you get an acceleration of 0.5456? Someone else double check me. Yeah? 0.5456? Now, Mac, we could go like this. D equals VIT plus a half AT squared. But what's VI? Which means even though this is a quadratic, this is the nice version of that quadratic, I can get the t by itself like I did in Physics 11. T is going to be 2 times d over a square root. We're going to finish up with this. You guys have been patient. It's going to be 2 times 30 divided by 0.543656, Mr. Dueck. Square root. Two times 30 divided by answer button and square root ailing, and I get, do you get a time of 10.49 seconds? This is what we wanted to find. What did they ask us to find? No, that's part B. What did part A want us to find? The rate at which heat energy was done. We said that was going to be friction times distance divided by time. Have I calculated the force of friction? Yep. Did they tell me the distance? Thank God. Have I calculated the time? Yep. But what can you get started with for homework now? Now, tomorrow, when do I see you guys? Next Tuesday. Lesson's going to last about a half hour, and you'll have the rest of class to work on this homework, a take-home quiz, and the review. So you can certainly do number 1. Two is good. 3 is good. 7 is good. 9 is good. 14 is good. You have been patient. Thank you.